Let's continue with some applications of midpoint theorem, and let's try to see what midpoint theorem really tries to tell about triangles. The line joining the midpoints is half the base and parallel to the base. This is midpoint theorem. What if I take a triangle? Okay, what if I take a triangle and I mark its midpoints and then I join? I know that this is parallel to the base and half the base, but I could take another triangle, okay, which has the same base as the original. As the original triangle, the pink triangle and the green triangle have the same base. And notice if I join them one below another, then this black line is also half the base and parallel to the base. So notice both the black lines are half of this base here in the middle, okay, half of the base, and they're parallel to the base, which means that these two black lines themselves are equal in length and they're parallel. But we know something, right? If you have two line segments that are equal in length and they're parallel, then the bounding quadrilateral is a parallelogram, which means that whenever you have this situation, right, the bounding quadrilateral here is a parallelogram. You can also keep this on top of each other like this. Well, it's not exactly visible here, but if you could keep it correctly, essentially, notice that again these two lengths will be equal and parallel, and the bounding quadrilateral will be a parallelogram. And the same thing happens here as well. This observation is called Varignon's theorem. So Varignon's theorem is generally stated in a very nice way. You say that if you take any quadrilateral ABCD, note that the quadrilateral need not be convex. It can be of this form. It can be A, B, C, and D. Okay. So it can be a concave quadrilateral or it can be a convex quadrilateral. Either way, if you mark the midpoints of the sides of the quadrilateral, and you form a quadrilateral out of the midpoints, that is always a parallelogram. Now, pay attention to this. It can happen that you have a triangle. So any triangle you draw inside, you mark it midpoints, and the midpoints of the sides of the original triangle, you get a quadrilateral that's a parallelogram. Now let's go back to the midpoint theorem configuration. Okay? Join C to M. Let's join the new thing here from C to M. By the way, the line joining the vertex to the opposite midpoint is called the median. Okay, supposing these two medians intersect at a point G. Now, remember Varignon's theorem? Look at this drawing and look at this drawing. Here also you have a triangle inside, just like this one. And that suggests that we can try to place this observation we have now into this problem, right? We can place it back into this problem. So what does that mean? It means that once you have a parallelogram, you have so many properties of the parallelogram that we have learned today, right? So if you go back, one of the properties of the parallelogram is that diagonals bisect each other. So we learn that further, notice P is the midpoint of BG. That's how we construct it, using midpoint theorem. P and Q were midpoints of BG and CG. So therefore, PG is also equal to PB and GQ is also equal to QC. So note something very interesting happened here. If you just focus on CM, you see that Q and G are a point of trisection. In other words, Q and G divide the segment CM into three equal parts. And similarly, if you look at BN, P and G trisect the segment and it divides it into three equal parts. So which means G is always a point of trisection. Okay, it divides the median in the ratio 2:1. Whatever this point G is, it divides it in the ratio 2:1. Here also divides in the ratio 2:1. Because you could have run this argument instead of with BC, you could have run this argument with AB, and the point of trisection is unique, the one that divides into 2:1. The same point must also be trisecting this line here, right? This median. So therefore, we can prove essentially from this argument that the point, because the point for S is unique, we can argue that all the three medians meet at a common point. Okay, and further, whatever this point common meeting point is, this divides the median in the ratio 2:1. Okay, so you proved two things here. In the next video, we will use these facts to show that the altitudes of a triangle are concurrent, and we'll discover the Euler line.